Hello, you're welcome to today's class. Our topic for today is techniques of differentiation. It is easy to recall that the derivative of a function provides us with the rate of change of that function. In other words, we are looking at derivative as being equivalent to gradient or slope in a graph. Now, what are the techniques? One of them is that when you're differentiating a constant, is actually equal to 0. When you're differentiating a sum, is actually equal to the sum of the derivatives. When you are differentiating a quotient, there is a formula for it. The numerator, you differentiate the numerator times the denominator minus you differentiate the denominator times the numerator all over the denominator squared, and so on and so forth. Now these are some specific derivatives. When you're differentiating power, you have n x raised to power n minus 1 and so on. When you're differentiating, natural logarithm of x is equal to 1 over x. When you're differentiating sine, you get cosine, and when you're differentiating cosine, you get minus sine, and the derivative of tan x will give us sine square x. Now let's look at some examples, the sum and the difference rule. Now if f and g are both differentiable, then differentiating the sum is equal to the sum of each of the derivatives, and taking the difference, derivative of the difference is also seen as the difference of the different derivatives. Let's take some example. Here A, I have differentiate the following: f of x equal to minus 2x cubed plus 9x squared minus 2. And for B, you have g of t equal to t raised to power 4 over 2 plus 3t raised to power 3 minus t squared minus 13t. How do you find the derivative? For A, solution is simple. You apply the power rule here and you have minus 6x squared plus. You apply the same power rule here and you have 18x, then differentiating a constant gives you 0. So in this case, you have to do the derivative component by component. The same thing happens for B. T raised to power 4 over 2. By the time you differentiate it, you have 4t raised to power 3 over 2 plus. You differentiate 3t cubed, you have 9t squared. And you differentiate minus t squared, you have minus 2t. And when you differentiate minus 13t, you have minus 13. Now the product rule. If f and g are both differentiable, now differentiating the product simply means you keep the first one, differentiate the second one, plus you keep the second one and differentiate the first one. It's as simple as that. Now let's look at this example. Now we should find the derivative of h of x, where you can see very clearly we have two products of polynomials. Now we'll call one of them f of x, and we'll call the second one g of x. And by the time you apply the principle of differentiation using the product rule, you're going to have that the derivative of f of h of x is equal to minus 24x squared plus 4x plus 15, as seen here very clearly. Now the quotient rule. If f and g are differentiable, then the formula for the quotient rule is that you keep the denominator, you differentiate the numerator first, minus you keep the numerator and differentiate the denominator all over the denominator squared. So that is the principle we are going to use here. So for this particular example, if y equal to x squared plus x minus 2 over x raised to power 3 plus 6, this is clearly a quotient, or what you can call a fraction, then the derivative dy dx will simply be what you are seeing here very clearly by applying this principle. And at the end, you're going to have minus x raised to power 4 minus 2x raised to power 3 plus 6x squared plus 12x plus 6 all over x raised to power 3 plus 6 all squared. You are actually going to get this if you apply this principle very carefully. Now we have the chain rule here. The chain rule says if y is equal to f of u is differentiable function of u, and u is equal to g of x is also a differentiable function of x, then f y is equal to f of gs is a differentiable function of x, and therefore the y dx is equal to the y du times the u dx. This is what we call the chain rule. Again, we are going to see some examples where you can apply these principles. Now, this example says we should differentiate the following functions when y is equal to square root of x squared plus 1, and we also have y equal to 3x squared minus 4 all raised to the power of 4. Now, the solution to the problem is this. For a, you say let u be the x squared plus 1 so that your y will now be square root of u. Now, you're going to differentiate u with respect to x and also differentiate y with respect to u. Then you take the product, and that gives you x over square root of u, which will eventually, when you replace your u with the initial assumption here, you're going to have x equal to square root of x squared plus 1. Now for b, you do a similar thing. You're going to replace 3x squared minus 4 with u, and once you do that, then you're going to differentiate u with respect to x, and you're also going to differentiate this y with respect to u. And when you do that properly, you're going to have 24x in bracket 3x squared minus 4 all raised to the power of 3. Now we have the derivative of logarithmic functions. You see, these are ln x is actually what we call the natural logarithm. So differentiating the natural logarithm with respect to x will give you 1 over x, and differentiating the natural logarithm u with respect to x will give you 1 over u times the u dx. Now let's look at this example. We should differentiate f of x, where your f of x is log 2 plus sine x base to the base of 10. Now, base of 10 is different from the natural logarithm. The natural logarithm is base e. Now, to use the chain rule here, we let u to be 2 sine x, then f of u will now be log u base 10. And by the time you apply the product chain rule here, you're going to get cos x all over 2 plus sine x natural logarithm base 10. Now, derivative of sine x and cosine x. When we started this course, we actually gave out some straightforward specific examples of how to differentiate trigonometries. Now let's look at this. Differentiate the following with respect to x. We have tan x, cosec x, sine s raised to the power 3, and 1 minus cos x all over sine x all squared. Now let's look at the solution. Here we express tan x as sine x over cosine x. Of course, that's what tan x is. And we apply the quotient rule here. So you actually know the reason. So applying the quotient rule will eventually give us cos x squared. Secant x squared, because secant is 1 over cos. Thus, tangent in this case will give us, differentiating tan x will give us sec square x. Now for b, what is cosec x? Cosec x is the same thing as 1 over sine x, so that we can write the derivative of cosec x equal to 1 over sine x. Again, we are applying the quotient rule here. Then you're going to have minus cosec x cotan x. What is cotan? Is cos x over sine x. And what is tan? Tan is sine x all over cosine x. So you have to really take note of all this. Thus, if y is equal to cosec x, then the derivative of y is equal to cosec x cotan x. Now we are going to look at C. Here we let y equal to sine x raised to the power 3 and let u equal to sine x. Then y equal to u raised to the power 3. And we apply the chain rule. you're going to have 3 sine square x times cosine x. Okay, and the last example, see here again, we let y to be this and let u to be the one inside. So y will now be u squared. Now you differentiate u with respect to x and you differentiate y with respect to u and take that product. It's as simple as that. So the y du here is simply 2u. Y du dx, which is differentiating this quotient here, will give us this long expression here. And at the end of the day, when you take the product, you're going to have 2 times 1 minus cos x squared all over sine x raised to power 3. Now, differentiation of inverse trigonometric functions. Let's look at some example. Differentiate the following. Y equal to arcsine 3x. And for B, you have y equal to arcsine x squared. And the third one is y equal to arctan 2x, 2 over x. So solution, if we set u equal to 3x, then y will be arcsine u. And again, you apply the chain rule, you are going to get 3 over square root of 1 minus 9x squared. For B, you replace x squared with u and you're going to have y equal to arc cos u, and the y dx will now be the y du times the u dx. And when you take that product, you're going to have minus 2x all over square root of 1 minus x raised to the power of 4. Now, let's look at C, the third example. So let u equal to 2 over x, then y is equal to arctan u. Now, you apply the same chain rule again. You're going to have minus 2 all over x squared plus 4. Now, our next subtopic is derivative of implicit functions. You find the dy dx in each of the following. X squared y minus 5x equal to 3. And for B, you have x raised to power 3 plus y cubed equal to 3xy. And x squared equal to y x plus y squared plus sine y equal to 3. Let's look at solution for A. We differentiate term by term with respect to x, treating x squared y as a product. That is, you have you keep x squared, differentiate y, dy dx, plus you keep y and differentiate x squared y, and you have 2x minus y equal to 0. And you now make your dy dx the subject here, and you're going to have 5 minus 2xy all over x squared. Note that this can also be solved by first solving for y and using the quotient rule. So I hope you can actually differentiate when to apply the implicit function derivative and when to apply the product rule. Okay. Now for B, here we treat y raised to power 3 as a composite function of 3xy. That's a product, that is 3x squared plus 3y squared dy dx will be equal to 3 in bracket x dy dx plus y when you factor out, and just the same method, you make dy dx the subject, and you're going to have y minus x squared all over y squared minus x. Then for C, you have you do a similar thing here, 2x plus 2y dy dx plus cos y dy dx. Now, all the dy dx, factor them out, then you have 2y plus cos y dy dx equal to minus 2x. And when you make dy dx the subject, you're going to have minus 2x all over 2y plus cos y. Now, differentiation from parametric equations. In general, if y is a differentiable function of t and x is also a differentiable function of t, then dy dx is equal to dy dt divided by dx dt. Okay, Now let's look at this example. Find dy dx if x is equal to t cubed plus t plus and y is equal to y y is equal to 2t squared. Now for b, x is equal to sine 2t and y is equal to cos 4t. Now we are going to find the derivative of those problems. Now solution, let dy dt equal to 4t and dx dt equal to 3t squared plus 1. So dy dx will be equal to dy dt divided by the x dt, which is equal to 4t over 3t squared plus 1. Now for b, let dy dt is equal to minus 4 sine 4t and dx dt equal to 2 cos 2t. Thus, dy dx is equal to dy dt divided by dx dt. So just like what we did earlier, we are going to have minus 4 sine 4t all over 2 cos 2t. Now, this other subtopic, maximum and minimum values of a function, you will see this is the graph of y equal to f of x. The point A, B, and C are actually called stationary points. Okay. Now this graph has two maximum here and one minimum point on x2. Now generally for any curve y equal to f of x, y is maximum when the double derivative is negative and y is minimum when the double derivative is positive. Now for point of inflection, the double derivative will be equal to 0, then you solve the problem. Now all the points A, B, and C are called stationary points on the graph or statutory values of y. Let's look at this example. If y is equal to x raised to power 3 minus 2s squared plus x plus 4, you find the stationary points of y. And B, the maximum and minimum values of y. That is a typical example. Now what you're going to do here from what we have stated is that you're going to differentiate twice. And when you do that, if it's negative, you say it has a maximum value. If it's positive, you say they have minimum value, and that is it. So the solution for A, dy dx, when you have done your first differentiation, you're going to have 3x squared minus 4x plus 1. At the stationary point, dy dx is 0. That is, you now equate your first derivative to 0, and you get to have x equal to 1 over 3 or x equal to 1 using factorization method. So the stationary points are x equal to 1 over 3 or x equal to 1. Now you take your second derivative of the same problem. You're going to have 6x minus 4. Now the maximum value of y is obtained when this double derivative is less than 0. This holds when x is equal to 1 over 3. So if x is equal to 1 over 3, you will now have 6 times 1 over 3 minus 4, and that will give you minus 2. And minus 2 is negative. So for that reason, the maximum lies there in 1.1 over 3. So the maximum value of y is 1 over 3 because it's negative at the point 1 over 3. Now you substitute back into the original equation and that 1 over 3, and you're going to have 112 over 27. So we've gotten the value of x, at the same time we've gotten the value of y. So when you plot x and y, it will give you the result you're looking for. So the maximum value of y is at this. Y has a minimum value when the double derivative is positive. That is when this is positive. This is true when x is 1. So if x is 1 here, you will see that you're going to have 2, which is positive. So the value of y when x is 1 is 4. So the minimum value of y is actually at 4. So what they are saying in essence is that this function has both minimum value and maximum value, as we saw in the introduction. Now let's look at take some higher derivative. Higher derivative means differentiating twice or differentiating 3 times or 4 times and so on and so forth. So it's possible to differentiate as many times as you wish. Let's take some examples. If y is equal to cosine x over 1 over sine x, find d squared y over dx squared. So this one is, you are asked to differentiate 2 times. Remember, this is quotient, so you're going to apply the quotient rule, and by doing that, you're going to have 1 over 1 minus sine x. Then you continue the second time, applying the quotient rule again, then you're going to have cos x all over 1 minus sine x squared. You see. Thank you for listening. Bye.